Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is Analytic Methods for Lawyers. Today's video is on classification with logistic regression. What we're trying to do here is to show how you can basically take some data, some covariates, and classify them as, in this example, one of two things, and we'll generally call it a 0 or a 1 or a true or a false, but you have a binary output. It can't just be any number as it is in traditional linear regression. There are a lot of ways of doing this, not just logistic regression, but I would say logistic regression is the most popular, and it's also a very good method. So I'm going to show you how to do that here, both from scratch in some sense and using the Wolfram language command logit model fit. I'll also show you at the end quickly how to emulate logistic regression using a simple neural network. With that, let's begin. And I'm going to start with a toy problem. In logistic regression, the y value is a random draw from a Bernoulli distribution, 0 or 1. And the Bernoulli distribution, as you may recall, has a single parameter. That's our coin flip distribution. But that single parameter can itself be the result of a function. With logistic regression, the function takes the following form. We start with probably a linear function, something simple like a plus bx, or maybe a plus bx plus cx squared, but some linear function where we're adding up terms. If you have two variables, it might be ax, a plus bx plus cy, and often these coefficients a, b, and c, they're not called a, b, and c. They're denoted as beta sub I, with I being indexed from 1 to n over the n variables. So here we'd have beta 1 and beta 2 instead of b and c. And beta 0 is this intercept term. By no means do you have to use beta. You could use smiley faces or whatever, some emoji instead. But I would say beta, for whatever reason, has become very popular in this area. The outer function in the composition is always a logistic sigmoid. If it's not a logistic sigmoid, then you got something else going on other than logistic regression. So basically, if we use Wolfram language notation, we can think of this as take your independent variables or your covariates, run them through, write a composition of linear function and a logistic sigmoid. So I keep saying logistic sigmoid, but what the heck is a logistic sigmoid? So let's take a look at one. And here's a picture of one. Basically, it's bounded between 0 and 1, just like probability values are. And if you don't do anything in particular, then it's going to be close to 0 as the x value is small, and close to 1 as the x value is 1. And it gets bigger as you move along. All right, let's take an example, and we're going to start with some very simple data, some toy data. And here's our toy data, okay? So it's just a list of 6 points, and you'll notice that the y value is either 0 or a 1. All right, now let's form a symbolic Bernoulli distribution. Here it is. We've got our linear function with those betas I warned you about, and then we're going to have a logistic sigmoid wrapping it. So it's a composition of a linear function and a logistic sigmoid. And then we've got, that's the sole parameter to our Bernoulli distribution. So what we want to do is we take a data point, we apply our logistic sigmoid to it, we then take the PDF of a Bernoulli distribution with that logistic sigmoid parameter, and we take the PDF of it for y. We're trying to figure out the likelihood, given a Bernoulli distribution with this parameter, that we will get y. And then, for reasons that we've talked about, it's often convenient, instead of computing this likelihood, to compute the log likelihood. So we'll call this function BDLS for Bernoulli distribution logistic sigmoid. Now, let's take our toy data and we're going to apply that BDL. Let's make sure that the Wolfram language kernel knows about BDLS. We're going to now apply BDLS to all of our data. So that gives us our log likelihoods. We're going to add them up, and we're going to negative it. So we're going to do what we've done a number of times in the past in working with maximum likelihood estimates, is develop the negative log likelihood of the set of data in toy. And we'll call that toy NLL. All right, so we have a symbolic expression which just has beta zeros and beta ones and a bunch of other glop in it that depends on the data, but that's really all we have. Now, what I'd like to do is show you what a surface looks like. What does it look like when I plot this for different values of beta 0 and beta 1? We can do that using the plot 3D command. Here's the range I'm going to let the betas vary over, and this is just some cosmetics code to make it look attractive, and I'll call my plot Toy Valley. All right, so there it is, and you can probably see that to minimize the log likelihood, we kind of want to be over there. I don't know, beta 0 looks like it's a little bit positive. Beta 1, hard to tell, not too far from 0. But we don't have to use our eyeballs. We can use one of those minimization functions that we've learned about in this course. I'm going to choose to use minimize. We're going to minimize toy NLL. And what are we going to minimize it for? We're going to minimize it for the parameters beta 0 and beta 1. And this will give us the parameters beta 0 and beta 1, which minimize the negative log likelihood of seeing the data that we see. All right, so there it is. And it turns out that we want to minimize it when beta 0 is 0.29 and beta 1 is 0.84. And what is that best negative log likelihood? It's 3.5051. Just kind of remember that number for a little bit. So if we didn't have minimize, we might want to use calculus. We've done this before. So look at the prior videos if this seems really strange. But we're going to take our toy NL, that's that expression up here with all the beta zeros and beta ones scattered throughout. We'll take the gradient of that expression with respect to beta 0 and beta 1. Then we will equal that to 0. We'll set the condition is that we want both those gradients to be 0. Then we'll use numeric methods because you can't find a closed form algebraic solution in this instance, and try to figure out for what values of beta 0 and beta 1 is this equality condition met. So let's do it. And looky there, it's exactly the same as we found using minimize. What we might want to do next is we now have some information. Where's the bottom? So let's put a dot at the bottom, a big green dot at the bottom of Toy Valley. And there it is. That's our minimum. And in some sense, you could just stop the video now and say, we're done. I've shown you conceptually how to do logistic regression. But I do think that you should watch the rest of the video because we're going to learn some important additional information. Let's get some statistics of our logistic regression. So remember we got that log likelihood, that negative log likelihood value. But we got that when we could take advantage of the x value information. That is our model up here, or up here, we're allowed to know what x is, and we're allowed to take that into account in computing the logistic sigmoid that feeds into the Bernoulli distribution. But what if we couldn't? What if we weren't allowed to take advantage of the x information and we had to just guess one number, beta 0, that did the best job if possible of minimizing the negative log likelihood? All right, let's do that little experiment down here. And I'm going to take our toy NLL expression. Let's just look at what that is. Remember, that's the thing which has all the beta zeros and beta 1s. And I'm just going to say, hey, plug in beta 1 is 0. So my beta 1s all disappear, and all I'm left with is an expression in beta 0. And now I want to find out, hey, what value of beta 0 minimizes the negative log likelihood of the toy problem subject to the requirement that beta 1 be 0. So let's see how this little cruddy model works out. Okay, so it turns out we do best when beta 0 is just about 0. And by the way, the logistic sigmoid of 0 is 1/2. And as it happens, if you look at the problem, if you look at the toy data, here's 1, 0, 2 zeros, 3 zeros. So they're half zeros. And therefore, it's kind of no coincidence that you might as well guess in the middle because the data is half zeros and half ones. Okay. All right, so what happened here? Well, by adding a parameter to our proposed model, that is by letting a parameter to the Bernoulli distribution vary according to the x value, we reduce the negative log likelihood from 4.15888, which is the best we could do if we weren't allowed to use the x information, to 3.5051, which is the best we can do if we are allowed to use the x information. So how far to perfection did we get? We got from 4.15888, which is really bad, to that 3.5 number. What would our value be if we were perfect? Well, if we were perfect, the likelihood of every entry would be 1. The log of every entry would be 0. Log of 1 is 0. And if I sum up lots and lots of zeros, I get 0. So best case we could possibly get if we had a perfect model somehow, which is sometimes called a saturated model, or at least there's a relationship between saturated models and perfection. We've gone some of the way between 4.15888 and 0. And in fact, we can kind of say, how far have we gone? So we could take this first value of toy best, which just in case you haven't forgotten, it's that 3.505 number, and we're going to rescale that number. Instead of going from toy null best, what's that? That's that 4.15 number, to 0. Let's have it go from 0 to 1. So if we were perfect, we'd get 1. And if our model was incredibly awful, we'd get 0. And we'll call this output McFadden. All right, we get 0.157. And that value of 0.157 is called a McFadden pseudo R-squared. Or it's sometimes called a McFadden R-squared. Or it's sometimes called a likelihood ratio index. Lots of names in statistics, often for exactly the same thing, and this is one thing that can make it complicated. But if you think about it, the McFadden R-squared, or pseudo R-squared for the purists, is conceptually similar to the R-squared in conventional linear regression. Let's think about why that is. In conventional linear regression, what we did is we said, what would the variance of the residuals be under a null model where we couldn't use our covariate information. We just had to make one guess. And so we got usually some pretty big sum of the squared residuals. And then we asked ourselves, what would we get if we had a perfect model? And the answer is, well, if we had a perfect model, every residual would be 0, and the sum of the squared residuals would be 0. And then we look at, well, how well did our model do with respect to sum of squared residuals? And basically the R-squared is how far along the way to perfection on that scale did we get? So it's really the same concept. That's why it's called a pseudo R-squared. The difference is that we're not using squared residuals here. We're using log likelihoods. Okay? And in general, we can think of one of these R-squared as a rescaling between our proposed model, our bad null, and we're going from a space in which the bounds are the null model, which is cruddy, the saturated model, which is usually awesome, and 0 to 1. And in often cases, our value of the statistic in the case of a saturated model is 0. As long as we're learning about the pseudo R-squareds, which are what you're going to use often to say, how well did our logistic regression do, we ought to learn about a couple of cousins. Because unfortunately, although everyone kind of agrees on R-squared in the linear regression world, there is not consensus on what to do in the logistic regression world, and before you just accept somebody's r squared in a logistic regression, you better find out what r squared are you using, because it can make at least a modest difference. So the distinction between the McFadden pseudo r squared and the Cox-Snell pseudo r squared is, instead of using those log likelihood values, negative log likelihood values, we're going to use the likelihood values. And if you think about it, the negative log likelihood, to go back from negative log likelihood to likelihood, first you're going to unnegative the thing. So we do that here and here. And then we're going to inverse log it, and the inverse of log is to exponentiate it. So the only other thing we flip is now null is in the numerator and proposed is in the denominator. And if that weren't all awful enough for reasons that I will not go into, you have to exponentiate that ratio by the number 2 divided by n, where n is the number of rows in the database. So that's your formula. You do not have to memorize that. And we're just going to compute it here. Here's our general formula. We're going to plug in the null log likelihood is from toy null best. The proposed log likelihood is from toy best 1, toy best, and n, we can just say what's the length of toy, how many data points were in toy. And there we go. There's our Cox-Snell pseudo r squared. And if you enjoyed the Cox-Snell pseudo r squared, you can't help but love the Krag-Euler pseudo r squared, which corrects a deficiency in the Cox-Snell r squared by dividing the result here, see that's the Cox-Snelly thing, by this correction factor. And so it will generally, the Krag-Euler will generally be bigger. Let's compute it for our data, and it's 0.2610. So again, if I want to show, ooh, look at my big R squared, I might use a Krag-Euler. If I want it to be a nice little, if I want it to be an eensy R squared, I might use McFadden or Cox-Snell. So you got to watch what people are up to. One more. Efren. Efren is easier. You pretend that you're dealing with linear regression, and you basically sum the squared residuals. That is, you look at what would your model predict minus what's the actuality. What probability would your model predict minus the actuality? And take the sum of the squares. Here I use the power total resource function that you all love. So here it is under the proposed model. Here it's what it would be under the null model, where I can't take advantage of the x information. I stuck a 0 in front of it. And how far from 1.5 to 0 is 1.21227. Here's my rescaling again, and it's 0.191. Okay. So you now know more than you ever cared to know about the pseudo R squareds for logistic regression. And my justification is you do need some measure to know if you've got a decent model or not. And these pseudo R squareds are a very powerful way of looking at it, because you're basically measuring how bad were my answers. So you need to know it. There's another way to think about logistic regression. Do you remember when we did linear regression, I showed you that maximum likelihood estimate was really the same thing as ordinary least squares if you made certain assumptions about the noise distribution? Well, again, with logistic regression, we can come up with a different penalty function and get the same result as maximum likelihood estimation. And there are advantages to doing things with a penalty function. The penalty function is one that we've seen already in this course, and it's one of the reasons I introduced it to you. It's cross entropy. It's a measure of the distance, not technically a distance measure, but it's like a distance between a source probability, also called a predicted probability, and a target probability. You can also call it an actual probability. So we're measuring the distance between the prediction and the actuality. So let's get that ramped up. We're going to have a target probability, and if our y value is 0, we'll call that 1, 0. I'm going to put the probability of a 0 being first and the probability of it being a 1 second. So we have a little probability vector here. But if y is not 0, in which case it's 1, then our probability vector is there's a 0% chance that it's 0 and a 100% chance that it's 1. Okay? So that's for the target, where we're expecting the target to, we're certain it's either a 1 or a 0. What about the source, also known as the prediction? So for this, we're going to use our friend the logistic sigmoid, and its value is going to be that beta 0 plus beta 1, and the probability that it's a 1 is this logistic sigmoid value, and the probability that it's a 0 is 1 minus the probability that it's this logistic sigmoid value. So that if you sum these values up inside the vector, you can probably see that that has to equal 1. So just so we understand how it works, let's take the point 0.31, and that's going to have a source probability of, let's make sure we get that evaluated. Okay, of the logistic sigmoid, the probability that 0 is 1 minus the logistic sigmoid of beta 0 plus 0.3 times beta 1, and the probability that it's a 1 is beta 0 plus 0.3 times beta 1. So we have a symbolic probability here. And with target probability and source probability under our belt, we can write a cross-entropy function. Cross-entropy is, this is our old cross-entropy formula or pipeline that we saw way back in the cross-entropy episode, and we're going to be applying that to the target and the source. Okay, so there we go. And then all we want to do is sort of combine these two things, and we'll have a point, and we're going to compute the target probability of the point and the source probability of the point. These are going to give us our two little probability vectors, and then we'll use the cross-entropy function defined up here to compute the cross-entropy. So we have a function cross-entropy from point, and usually what we want to do is we want to take that cross-entropy from point function, map it over all of our data. Here our data is called toy, we saw it before, and then we generally want the mean cross-entropy. What we want to minimize is the mean cross-entropy. We could also minimize the total cross-entropy, same thing. Remember that discussion about monotonic transforms and optimizations that I went through in an earlier video. So here we will compute an expression for the mean cross-entropy of all the data. We'll call that means. There it is. It's a symbolic expression in beta 0 and beta 1. And when you see a symbolic expression in a few variables, by now I'm hoping you're thinking, when's he going to minimize it? And that's what I'm going to do right now. So we're going to minimize the cross-entropy. That's what we're going to do. And what are we trying to do it for? Not A and B. That was what it was in an earlier draft when I was using A's and B's instead of beta 0 and beta 1. And so, here we go. All right. We get it's minimized. The cross-entropy is 0.584184. What are the values? Beta 0 is 0.29, blah, blah, blah. Beta 1 is 0.837. And where have we seen those numbers before? Let's go right up to here, right there. And it's the same thing we got when we used the negative log likelihood. We took the gradient, we set the gradients to 0, and we found out what the values were of beta 0 and beta 1 that solved those equalities. And it's also the same value we got when we simply asked the computer to minimize it. I just showed you how to do logistic regression from scratch. Now, let's show you how to do it the easier way, now that you understand the concepts. And the function here is logit model fit. It works basically exactly the same as linear model fit. So let's use it on our toy problem. Logit model fit. First argument is the data. The data needs to be in the form of a matrix in which the last column is the dependent variable, and the remaining non-rightmost columns are the independent variables or covariates. We have our basis functions here, and we have our variable that's in the basis functions here. And we do that, and we'll call our result LOMF. There's good old LOMF. We can find out what properties we can learn about LOMF. And it turns out that there are a lot of properties that are inside this object. Let's get a couple of them under our belts. So let's look at things like best fit parameters, function, log likelihood, likelihood, ratio, index, Cox-Snell, pseudo R squared, Craig, pseudo R squared, Efron, pseudo R squared, and something called the deviance table. Let's do it. All right. So this is our best fit formula. It looks exactly like what we got before. Here are our best fit parameters, exactly what we computed by hand. Here is this fit expressed as an anonymous function. Here's that log likelihood that we computed. Remember that number, our negative log likelihood was 3.5, so our log likelihood is negative 3.5. You remember that McFadden pseudo R squared, and I told you it was sometimes called the likelihood ratio index? There it is. Remember the Cox-Snell pseudo R squared? It's exactly the same value as before. Same with the Cox-Euler pseudo R squared. Same with the Efron pseudo R squared. But now at least you know what they mean. And finally, we have something called the deviance table. The deviance table is asking, okay, what is twice the log likelihood if I use nothing in my model? And remember we got that number 4.15 something? Well, if you double it, you're going to get this 8.317 number. So this residual deviance is closely related to the null log likelihood. And similarly, remember that 3.5051 number? Well, if you double it, you get this value. And so the deviance table, which I'm not going to spend too much time on today, but it does contain indirectly information on our log likelihoods for different models. Perhaps the most important table, though, that we usually want to look at is the parameter table. This has the same role in logistic regression as it does in linear regression. And here it is. It's important enough. Let me magnify it for you. All right, there it is. And so basically these are our coefficients again. These are our standard errors. If we divide the estimates by the standard error, we get a z statistic. We can look, the little computer looks up the appropriate normal distribution, and from that it computes a rarer probability, and that rarer probability is, as it turns out, the p-value. And so for what it's worth here, we could not readily dismiss the null hypothesis that the true value of the parameters here was 0. With 6 data points, we don't have a heck of a lot of data. So let's go back to an unmagnified view of the world. All right. So, although, unfortunately, one of the things that's not in our fitted model object is the actual probability distribution of the parameters beta 0 and beta 1. We can construct that. We know for the null hypothesis, by sort of the definition of the null hypothesis, the mean of the distribution is going to be 0, 0. And as it turns out, we can compute the covariance of the multinormal distribution here by asking it for the LOMF covariance matrix. So this is going to be the distribution of the parameters under the null hypothesis. We've got that. We can then take the marginals of that multinormal distribution. So let's do that. First normal is this normal distribution. The second the first marginal is this normal distribution. The second marginal is this normal distribution. Where have we seen these numbers, 0.958 and 0.794 before? Looky there. There they are. Those are the standard errors. So these standard errors aren't coming out of the blue. They're actually parameters to the distribution of the coefficients under the null hypothesis. And so we could actually see where they get those p-values from. And I told you it's the rarer probability. So let's just do that. And chunk. It takes a moment because rarer probability is a little bit complicated. And we get these values 0.7595, 0.291538. Look at that. Same thing they got over here. So this is telling you, where does this stuff all come from? And the idea, again, is what a regression is really doing is it's producing a probability distribution associated with the null hypothesis. It might be producing a probability distribution associated with the data, but in any event, it's that probability distribution that's being used to compute these standard errors, associated statistics, and therefore the p-values. Let's do something a little more complicated than the toy problem. Let's try to come up with a model that predicts whether you were going to live or die on board the Titanic, which went down in 1912 and produced many movies. All right, so let's get the data. There's our data. It's a built-in data set. You can use logit model fit sort of within the data set framework, but I'd have to teach you something else, and I don't feel like doing it, so let's get it into a different form as a matrix. I don't think this code is very interesting, so just trust me. I'm diddling with the structure of the data set here, and finally I'm going to turn it into a matrix, and we're going to call that matrix Titanic Training Matrix. So here's some of the data, and it's a 1046 by 4 matrix. Okay, so there's our data. Let's run logit model fit on it. Logit model fit, first argument's our data. First argument is our data. Second argument are our basis functions. We want to be looking at an intercept term. Cabin class, age, and gender. Our variables are cabin class, age, and gender. We do need to tell it that cabin, in first, second, third class, is a nominal or categorical variable, and gender, female, male, is also a categorical variable. No fluid genders in this data set. So let's do it. We're done, and we can find the various properties. Here what I've done is cleverly highlighted in orange the properties that are available to you in a logistic regression that aren't available to you in a linear regression. We're going to do that same thing again where we look at the best fit parameters and the function. So that's the equation of whether you were going to survive on the Titanic. I'll talk about discrete indicator in a moment, but just know that there are formulas there. And we can look at the parameter table. All right, so let's take a look and figure it out. Who lives, who dies? Being a woman definitely helped you survive. Remember, we can think of these estimates as updating the log odds of, in this case, surviving, and our p-value is essentially 0. Age is a negative, but not a huge negative on a linear basis. Statistically significant, yes. Being in first or second class was a good thing. Being in second class was almost as good as being a woman. And we don't, basically being in third class that's sort of our base level, not so good. And so that's what affected in this simple model whether you lived or died on the Titanic. Again, we could look at the distribution of the coefficients here. I'm not going to look at the null distribution. I'm going to update it with what we actually found. So this is kind of what we expect. And we can take the marginals. We can form a confidence interval and say how confident are we that the true value would fall within this zone. I'm going to use quantile, which you might want to remember how that works. And I'm going to be looking at the 2.5% quantile, the 97.5% quantile, so we have an equal-tailed 95% interval here. That's what we get. And I wonder if we could just have gotten that directly with all this fuss. And in fact, we can. If you look, these numbers match up exactly to the confidence interval that's determined directly from the fitted model object. So this is telling you, okay, you got 2.28. Is it really 2.28? Well, no, it could be 2.26. It's unlikely that it would be 1.81. That would be pretty unlikely, or that the true value is 2.97. That's unlikely as well. Okay, and that is the mandatory component of this video. There's one other thing which I'm going to show you as an option, which is understanding logistic regression as a neural network. And then, although I'm not going to narrate it, you should notice that at the end of the notebook that's associated with this video, there is a discussion of that discrete indicator function thing that you saw up here in trying to describe the, not for here, where is it? It's for the Titanic. In trying to describe the, here we go, best fit. Okay. As I said, we can also understand logistic regression as being a special kind of neural network. And I think even though we haven't studied neural networks in any depth yet, it's interesting even at this early stage to kind of see the relationship between what might be thought of as two very different problem domains. So neural networks have architectures, and this is a very, very simple one. This is like the complete opposite of many modern neural nets. We have one input value, and we want to get out a probability that the output is a 1. And we then want to minimize the cross-entropy loss between what our model says is the probability that it's a 1 and whether it's really a 1 or not. So we're going to construct this. Neural networks, as I think I've mentioned in other videos, have layers. And our first layer is a linear layer that's going to take one value and produce one value. The single value coming out of the first layer is a linear function, one linear function of the inputs, in which case it's just one input, just a number. We're going to take the output from that first layer and then run it through a logistic sigmoid function. And if you think about it, what I just described is exactly what I said about logistic regression. We take our data, the independent variables, we compose it, and we run it through a linear function and then through a logistic sigmoid. And the only difference here is instead of saying function, I say layer. Okay? That's really it. Then what we're going to do is we're going to take a cross-entropy loss layer, and that's going to compare the probability vector coming out of the logistic sigmoid layer with the probability vector that comes from the target port of the data. And that's the architecture. And what's going to happen when the net is trained is it's going to fiddle with the coefficients inside this linear layer here until it minimizes the cross-entropy loss. And we know from above that minimizing the cross-entropy loss is a way of finding a maximum likelihood estimate for the parameters of the logistic regression problem. So let's actually build this. The neural net's going to need layers, a connectivity structure, and some information on the ports. All right, so we've got our 3 layers. This is basically an association where we name the layers and then we say what kind of a layer it is. It's a cross-entropy loss binary. Binary means the data coming in is going to be a 0 or a 1. Very simple. Here's our connectivity structure. It's very simple. It's just a pipeline. The linear layer goes to the logistic sigmoid layer, which goes to the loss layer, that cross-entropy loss. What's going in? We've got a scalar, meaning a number going into the input, and a scalar, meaning a number going into the target. So now we can construct our net graph. A net graph has the layers, it has a connectivity structure, and it has the ports, and don't worry about the sequence, at. All right, and this is information. Full summary graphic is going to give us a nice picture of our network. Okay, there it is. And we can see we've got input. The input goes into a linear layer. which is fed into a logistic sigmoid layer, which is fed into one of the ports of the cross-entropy layer. The cross-entropy layer's other port is the target information that does the little computation, and out pops a loss. So it's kind of like a diagram of a computation. It's very nice. All right, what else do we need? We need to get our data in the right form. Unfortunately, machine learning in Wolfram language requires a different form than statistics. So instead of having a matrix in which the dependent variables in the last column, we need a list of rules in which the covariates, the independent variables, go on the left-hand side, and the answer, which here is a binary, 0 or 1, goes on the right-hand side. And what will happen is that the neural network will take the left-hand side and say, oh, that's what you want to go to the input, and it'll take the right-hand side and say, oh, that's what you want to go to the target. So let's actually do this. Let's put our data in the right form. There's our little toy data. And now let's do our training. Our training should not take long because this is a very simple problem. The arguments to net train, which is what you use to train the network, is our architecture, our data in the right format, and this optional argument is what do you want back, and I want to get everything back because I like everything. So let's run it. It's running away, ka-chunk, ka-chunk, ka-chunk. It keeps running this data through and adjusting it. You can learn that it's using something called an atom optimizer. It's only one little CPU. Real neural nets tend to work on multiple GPUs, but this is a very simple problem, and I could have this thing done already. You can see perhaps that we're not actually gaining anything right now. All right, it's done. We've got our net train results object. Let's pull out the weights and biases out of that first layer, that linear layer. There we go. Those are the numbers we have. And let's see what our parameter table says. Our parameter table has these estimates of what the parameters should be, 0.293166, 0.837617. And so what we see is that a neural network is capable of emulating logistic regression and much more. That brings me to the end of this video on classification using logistic regression. We'll see classification again, we'll see logistic regression again, but hopefully you're going to begin to understand the power of this tool.